organic chemistry is just some interesting introductory stuff about it, because it's one of my favorite courses I've ever taken. It's also the reason I became a chemistry major, because I loved organic chemistry so much. So, hydrocarbons are molecules made of carbon and hydrogen.
How much do you want us to write?
You don't have to write anything.
Anything?
Just pay attention. And there's lots of things that we use them for, like notably fuels, but also like making plastics and tons of things. Like if you look at like petroleum and petroleum products, there's so many in the world. So many petroleum products we use. We're going to talk about the simple ones, and how we name them is based on the number of carbons. And how they bond is the suffix. So, and other functional groups we'll talk about, and a couple of them you may have heard already. But the prefixes, or the prefaces for the carbon compounds, it goes meth, eth, prop, but, pent, hex, hept, oct, non, dec. So it's based on the number of carbons. So if you have a prefix with something with 8 carbons, it's oct. And if it's all single bonds, it's going to be octane. It's called an alkane. So if you have all single bonded carbon, it's going to be like ethane, methane. Propane is one that you commonly see. That's C3H8. It's all single bonded. When you add a double bond in there, it becomes an alkene. So like if you have 4 carbon molecule, like we did in our POGO, with a double bond in it, that becomes butene. Hexane is 6 carbon with all single bonded, but hexene is 6 carbon with a double bond. And if you have a triple bond, carbon-carbon, that's called an alkyne. So the ending would be ione. You can actually have more than one double bond in there, and then become like pentadiene. So you could have more than, if you needed more than one double bond. So naming is fun. If you guys want to talk more about naming stuff, I'm good at that. We'll talk about that a little bit later. Saturated hydrocarbons. Now, this is actually an important thing. So if you ever have something where you have a number of carbons, and more than twice the number of carbons for hydrogens, you have a saturated hydrocarbon. So, for example, like this, think about it this way. So my end carbons, my last carbons are going to have 3 hydrogens attached to them, right? That's the mass. So that's where your 2n plus 2, your 2n comes from. Okay? So you have 2 hydrogens for each carbon, and then 1 extra hydrogen for each end carbon. That's this one. So for this one's another one. You have 2 hydrogens for each carbon in the chain, and then 1 extra for each terminal hydrogen at the end. So that's why I have 2n plus 2. So that means that you have as many hydrogens as possible. So there's no more possibilities of adding anything more in there. Unsaturated hydrocarbons, unsaturated meaning not full, you can have more hydrogens come in there. So if you have any sort of hydrogen to carbon ratio where you have less than 2n plus 2 to n, you're going to have a way that more hydrocarbons can go in there. Guys, eyes up here. Just pay attention. Okay? So, for instance, if you have a double bond like C2H4 or C6H12, you see the carbon-to-hydrogen ratio, and this one is 2 hydrogens for every 1 carbon. So it's less than 2n plus 2 to 2, or 2n plus 2 to n. Same thing if you have a ring structure. This here is it's all single bonds, so it's called it's a hexane. And how they say it's in a ring, they call it cyclohexane. So cyclo meaning ring structure. All right. So these are examples of unsaturated hydrocarbons. Cis-trans isomer, which we talked about in the POGL, is across a double bond. Has to be a double bond. These here, single bonds, you can have free rotation. So these are the same molecules. So it doesn't matter how you make them if there's a single bond. But when you have a double bond, you can't freely rotate. So you have your trans isomers, which are across from each other, Opposite side of the carbon-carbon double bond. It's like a transcontinental highway. A highway that goes across the continent. A transatlantic flight across the Atlantic Ocean. Trans meaning across. Cis, I don't know where that came from, but it means the same side. So if you have them on the same side of that carbon-carbon double bond, sister carbons. I like that. I like sister with a C. I like that. That's good. So they're a different type of isomer. There's that specific name. Not every isomer is cis-trans, but it's a certain example. So this guy right here, you have a carbon-carbon double bond, but you have this carbon on the same, the chlorines in the same carbon. That's just called 1,1-dichloroethane. Oh, ethene. Oh my goodness, I'm sorry. That should be an E. Dichloroethane. I hope you guys can forgive me, please. Ethene. All right, let's just get off this slide. So this is another one we did in the Pogo. So guys, I think this is number. I think it's on the. I think it's on the second page. So C4H8 on the bottom of the second page. We talk about the non-ring structures of C4H8. So here you can make it a bunch of different ways. You can make cis-2,3-butene. The 2,3 refers to where the double bond is. So it's between the second and the third carbon. So cis-2,3-butene. And this is trans-2,3-butene. You can make them in two different ways. You can have the CH3 groups, the methyl groups, on the same side of the double bond or on opposite sides of the double bond. You also have 1,2-methylpropene.
Wait, is it reading from right to left?
Either way, it's arbitrary. So you can have this is it. So for this one, you can have 1,2-methylpropene. Or that'd be 1,2-methylpropene. Sorry, I think I might have named that a little bit wrong. But
Would it be 3,4?
no, because you always start with the functional group. So this would be 1, 2, 3. You say it's a 1, 2, 3. You start with the fun stuff first.
Down first or up first? Or
It doesn't matter. You start, since the double bonds between here and here, you say that these are the first two carbons. Okay? So this is not cis or trans. This is a different type of isomer. It's neither cis nor trans. Where you guys see this is like fatty acids, so like your oils that you have for dinner when you're cooking with olive oil. Fatty acids have this organic acid part, which is COOH, which is why we call acetic acid CH3COOH sometimes, because of that organic acid. That means it's organic acid. So, and then they have a hydrocarbon tail. So saturated fats are like saturated hydrocarbons. The carbon tail has no double bonds, no ring structures. Unsaturated fats, and this is big. We talk about it all the time. You know, you have your saturated fats, which are your like animal fats, and they tend to be less healthy for you than your unsaturated fats. And the reason why is because they're less soluble in water. They're harder to digest, and and you can't do as much with them. Unsaturated fats have one or more double bonds, and you hear this stuff about trans fats all the time, right? You hear them in the news. Now, cis fats are found in nature, like almost everywhere. I don't know if there's any examples. There probably is, but almost every fat that we eat is a cis fat, and natural. When you make them like they did, they used to for like mass production, they would have cis and trans fats. So that's why, you know, trans fats are linked to higher rates of cancer, and that's when you have when you have the fat chain, when you have the carbon groups on opposite sides of the carbon double bond. When they're on the same side, they're healthier for you. When they're on opposite sides, they're not. When you also hear the term monounsaturated fats and polyunsaturated fats. So monounsaturated have one double bond, poly have more than one double bond. So you can have all sorts of different length chains. So like the reason why they're so different is because of how that cis-trans isomer can affect the shape of the overall molecule. So the oleic acid has a cis double bond here, where you have the groups on the same side, whereas alaitic acid has them on the opposite sides. And these end up being much harder to digest than these guys, and they have different properties. Like these tend to be a lot more. The IMF is stronger in the oleic, in the cis fats than the trans fats because they can get closer together. So that's an interesting fact. So here's another. This is cis oleic acid and trans. So the trans ends up being a lot more like saturated. They look a lot more like saturated fats than the cis right here. And these are just better for you. And there's another IMF thing. So these are much more representative of saturated fats. So see how this trans fat looks a lot more like saturated fat than the cis? So you have that bend here in the cis. You don't have that in the trans. Okay. I guess I have too many slides. Alcohols are functional groups that have OH on them. Not OH minus. Okay, I noticed a lot of that on the IMF quiz. A lot of people had CH3OH as an ionic compound. Not the case. When it's an ionic compound when you're with a metal. CH3 plus is not an ion; it's molecular. So this is not hydroxide ion. So they're actually not basic at all. And on the contrary, they tend to be more. Very, very, very slightly acidic. Very slightly. So most of the time we consider them neutral. And we'll talk why later. So anything that you have with that OH minus functional group attached to a hydrocarbon makes it an alcohol. And those alcohols tend to be soluble. So like actually ethanol and like isopropanol and propanol, they're all almost infinitely miscible with water, meaning that you can add as much as you want and it'll mix together. Like there's no saturation point. Organic acids or a carboxylic acid is a CO double bonded and then an OH on there. So this is actually not an alcohol. When you have a double bonded O there, it becomes an organic acid, a carboxylic acid. So this here would be called ethanoic acid or acetic acid.
But isn't that an alcohol on the bottom?
But when you have that double bonded O right there, it makes it something different. So when you have the OOH, you see you have C, O, and then OH, it changes it differently. It makes this acidic. It makes this an organic acid. So acetic acid is an organic acid. Ketone is something where you have a carbon-oxygen double bond in the middle of the molecule. So this here is a ketone. It has to be a non-terminal carbon. So like if it has to be a carbon in the middle. It wouldn't be a ketone if it was on the end. Aldehydes are when you have that OH group in the end. So you have CHO double bonded to the carbon right there. That's like formaldehyde would be CH3O or CH2O. Yeah, right.
What does I stand for?
Just a different hydrocarbon group. It's just a replacement group. Like it can be a hydrocarbon, or it can be another alcohol, or it can be some other different organic group. But like it's some number. Like in this case, R would be CH3 because you have CH3 attached to that COH right there. Okay. Ethers are interesting. They're fun. You have an O, like these are similar to water, and we talked about these a little, like when we compared dimethyl ether in the POGL, we compared that to ethanol. Like here, this is an ether because you have an oxygen in between R groups or carbon groups. So here you have a 1 carbon group and a 2 carbon group attached to an oxygen in the middle. So the prefix for 1 carbon is meth. The prefix for 2 carbon is F. So they call this methyl ethyl ether. So that's why it's called that. And here we have a little bit more. You talked about like amino acids too. Like an amide is a group where you have a nitrogen in there. You don't worry about these. You won't see these too much until you take. Actually, you probably will when you take AP Bio or AP Chem, or if you take organic chemistry in the future. So I think it's worth talking about this. That's it. So I hope you guys enjoy this. Sorry, juniors, you had to miss this.